I think this started from digital information that Sherry spoke about a little bit, and Shannon and von Neumann in the 40s, and has led to all sorts of discoveries of where we can find computing. Everything from billiard logic to bubble logic to DNA logic, even the way that we describe synthetic biology in terms of logic and circuits. And now synthetic biology itself is an unprecedented ability to program biological materials to have functions that weren't necessarily found phenomenon, but now have exciting new opportunities in that specific materials, or chemically program, in that case was protocells. And I think one of the most exciting opportunities is in DNA nanotechnology, where we can actually build three-dimensional structures for a variety of applications. We heard some of that earlier today. Yep. I got a lot of slides to go through. Okay, I'll try to slow down. Sorry. This is sort of just setting the stage, and then I'll show a lot of my work. But in terms of materials as well, there's a new opportunity to be able to program materials to have different transparencies, reconfigurability, and some of the tools that Max had described, not in terms of the 3D printing, but software is now finding its way into DNA nanotechnology, where Autodesk is teaming up with a group from George Church's lab to produce CAD Nano, a 3D CAD software for DNA to build 3D structures. So I think this is sort of a parallel phenomenon, or a parallel moment in the design community, where there was this convergence of what you can design versus what you can build. And especially at the large scale, these two roads were sort of forking. If you look at the architectural community, what has software and the ability to program things, what has that given us? That has given us massive iteration. So we've been able to produce many, many versions of our software, or of our geometry, geometric complexity, describe computational problems, generate simulations for physical phenomenon. This is a project we did at the Guggenheim, simulating magnetics in the void, which was basically the idea of you're always competing between the artwork and the void. So we simulated this magnetic moment. You can analyze things, so you can analyze structural loading or environmental loading based on the geometry you've produced. You can then take that geometry and detail it, number of rivets, bolts, text, nomenclature, and then you can send that to, hopefully this video shows, you can send that to machines, and you can cut out that material. So computation and programmability has allowed us to go from design conception to analysis, all the way to communicating with machines. This is a project that was built, the parts you were just seeing, for the 150th anniversary of MIT. But what I didn't show you was this moment. So this is the moment when we're bleeding, when we're bruised, and we're forcing these things together. And I think this is the moment when we can take hints from all of these other disciplines, and we can try to converge the left side of the screen with design, analysis, fabrication, with the right side of the screen, which is assembly. And at large scales and construction scales, assembly has been left out of that equation, where there is no programmability, there is no computation in assembly. It's brute force. It's manual labor construction. So my work tries to address that. And I think there's two ways to go. One way is that you can automate it, and you can try to replace the user and try to just purely automate it. The other way, which is what I'm trying to focus on, is that you can embed information into materials, and you let the materials build themselves. So if we want to have self-assembly, similar to what we saw in the biological or chemical examples, if we want to have that at the large scales, what do we need? So we need 4 key ingredients. The first ingredient is you need blueprints. That's essentially the code, the A, C, T's, and G's, the amino acid sequence, the left, right, up, down. Then you need programmable parts. So programmable parts are on, off, connected, disconnected, on the ground, off of the ground. Third, you need energy. Energy is the way you get from point A to point B. And fourth, you probably want error correction in order to get the structures that you actually desire. So I'll show a bunch of projects that show some of those characteristics, sort of mixing and matching, testing them out. The first one are reconfigurable chains. So they're one-dimensional strands, just like proteins that fold into three-dimensional structures. This one is looking at a number of units. So these are 3D printed units. you orient those units in a different way. So you can go right, left, up, down, and that gives you a code. So that's the program of your three-dimensional structure. And it folds from one-dimensional into three-dimensional shapes by random shaking. Hopefully a video will show. Thinking about it. So basically you take this flexible chain, you shake it randomly, and by shaking it randomly it gives you non-random structures. So that means the energy is activating it, going from 1 dimensions to 3 dimensions, and you have a program which is the sequence of your parts. The second version of that, we're now using that to describe protein folding. We have a very simple protein, the Kramden protein. This is a collaboration with a molecular biologist. And we're looking at how does one-dimensional to three-dimensional self-assembly describe the process of protein folding. What can we embed in there? What can we learn about it in these tangible models? Can we play that video? You might need to click on the screen. Let's see, play. Can you click? Where's play? Okay, so basically it's a single strand. There's a three-dimensional molecular structure that was given to me by the molecular biologist, Arthur Olson. He has a molecular modeling software. So he sends me this geometry. I can decode the geometry into a strand of angles, and then that strand is linked up to an energy source. So we've tried it with magnets, we've tried it with water, heat, you can do sound, any energy source that you have, and you can fold this one-dimensional into the full three-dimensional structure of your protein. So it has all the helices. Right now it's a single strand, so we don't have cross-linking. You can bias it by having different weights to the magnets. So we're also looking at how that can translate into 2 dimensions. So you have sheets that fold, basically like self-folding origami. Next slide. And then a whole separate family is looking at how you have autonomous self-assembly. So you have separate parts, not pre-connected. There's 3 key ingredients here which kind of encode those 4, which is geometry, attraction, and energy. If you change the geometry or the attraction, you can change what you get in the end. This was done with Autodesk for the TED Global Conference. We built 500 of these beakers. I have a beaker, so afterwards I can show you it. And basically in each one of the beakers there's different molecular structures. There's a poliovirus, an enzyme, different colors. Can you play that? You have to click on it. And so basically the participants at the conference could walk away with one of these custom beakers. So you take it, you shake it, it's going super slow, not sure why, but you shake it, normal speed, not slow motion, and it self-assembles into a 3D structure. So you get your molecular structure randomly shaking it. Let's move on. Okay, so we tried a larger version at the TED Long Beach conference, and the idea here was, can you build an installation that builds installations? And so we built furniture scale objects. So these were 24-inch diameter dodecahedrons, and they populated this square, so you could all sit on these. These would basically be like building a machine that would make our furniture for us for this conference. And so the users would come up and they would spin this machine. It was roughly 20 feet in diameter, or sorry, 20 feet in length. And you would spin this machine, and you would then make these furniture scale objects. So it's sort of like manual labor, making your own chairs. Can you play that? Actually, let's go to the next one, just for sake of time. Can you play that one? Yeah. So this is another version of that one that we sent to Sweden. Let's see if it'll load. Looks like their computer's jammed up. Play. Okay, so we sent this one to Sweden. It's sort of a desktop scale version of it. Maybe it'll play. So you spin it, and eventually it self-assembles, and because the movie is playing so slowly, it's not going to be very smooth. But generally you get the idea. So separate parts, you give it some energy, and it builds the structures for you. So the idea here is that you embed all of the assembly instructions into your material parts. You give them some sort of energy source, and they self-assemble for you. We can skip the video. It's not working so well. Next slide. Can we go to the next slide? Click there. Click underneath the video. Yeah, at the bottom of the screen, yeah. Just click in the black margin at the bottom of the screen. Down, 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 down. Move the cursor down. Yeah, click at the bottom. Can you move your cursor all the way to the bottom of the screen and click? Move the cursor down. Okay, good idea. Right here. Click right here. This will advance the slide. All right, not working. I think your machine's frozen. Okay, well, anyway, the idea is that you have discrete parts, you want to embed information, and you want them to build themselves, or you want them to have some collaboration with the assembly process. So can we have computation that goes from the design and conception idea to analyze them, to build the parts, to then assemble the final structure that you want? So it's embedding some information and decision making into physical systems.